Okay, so now we've moved on to the final area of study on Laplace, which is looking at a very fascinating subject on convolution. And it's fascinating from many perspectives. In terms of what it actually is, it's quite interesting to understand what convolution is. But the importance of convolution and how it ties into inverse Laplace transforms are equally fascinating as well. And once you understand the principles of convolution and you can convolve two functions together, you'll have a tool that will enable you to find an inverse Laplace transform of two products, almost no matter how complex or difficult the products are. Up until this point, we've been using the method of using partial fractions and splitting an inverse Laplace operation into a series of components, each component being split into its partial fraction. And using the principle of linearity, we were able to say that if the inverse Laplace transform of a very complicated function was whatever it was, we could just split that up into individual components and then sum them together, and that would be the same. But what happens when you can't do that, or you don't want to find a whole series of partial fractions? So that's when the theory of convolution comes in to its own. So before actually looking at what convolution is, I'd like to have a look at a property that we see with inverse Laplace transforms in general. So we said before, and this is where we're going to challenge the property of linearity. We said before that if you have the Laplace transform of f of a, and you want to know what the, and let's say we have the Laplace transform of f of b, we said that the Laplace transform of f of a plus the Laplace transform of f of b is identical to the Laplace transform of f of a plus f of b. So just to reiterate that, and I'm going to go through this very, very slowly because I want to be as clear as possible, and convolution is a fairly challenging topic in Laplace, so I'm going to labour on these points, and I'm going to repeat things as well. And it's the kind of topic which I found that I needed to go over quite a few times before I really understood what it was. So again, if we have the Laplace transform of f of a plus f of b, that's equivalent to the Laplace transform of f of a plus the Laplace transform of f of b. Now, does that mean, based on the principle of linearity, that the Laplace transform of f of a times the Laplace transform of f of b would be identical to the Laplace transform of f of a times f of b? In other words, the question is, will the Laplace transform of f of a times f of b be equivalent to the Laplace transform of f of a times the Laplace transform of f of b? And the answer is no, it's not. And this is where the linearity principle breaks down, because what we find is that the Laplace transform of f of a times the Laplace transform of f of b equals the Laplace transform of the convolution of f of a and f of b. In other words, the Laplace transform of the convolution of f of a and f of b is identical to the Laplace transform of f of a times the Laplace transform of f of b. And therefore, we can say that if we take the inverse Laplace transform of two products, of, let's say, we take the inverse Laplace transform of the Laplace transform of f of a times the Laplace transform of f of b, that will give us the inverse Laplace transform of the Laplace transform of the convolution of those two functions. In other words, that will result in purely the convolution of those two functions, because the inverse transform of a forward transform cancels the Laplacian operation, and therefore it's going to equal the convolution. I'm going to say that again, and then I'm going to write it down. And again, this is something that I really had to go through many times before this was clear. So I'll say that again. I'll try and be a little bit clearer. So if the Laplace transform of f of a times the Laplace transform of f of b equals the Laplace transform of the convolution of f of a and f of b, then we can say, taking the inverse transform of both sides, we can say that the inverse Laplace transform of the Laplace transform of f of a times the Laplace transform of f of b will be purely the convolution of f of a and f of b. And what that allows one to do is solve two products, the inverse transform of really any two products, just by finding the inverse transform of each individual function and convolving those two functions. So let's see what that looks like on paper. So we said that the Laplace transform of f of a plus the Laplace transform of f of b equals the Laplace transform of f of a plus f of b. Yep. What we can't say is that the Laplace transform of f of a times the Laplace transform of f of b equals the Laplace transform of f of a times f of b. We cannot say that. Rather, the Laplace transform of f of a times the Laplace transform of f of b actually equals the Laplace transform of f of a star or asterisk f of b. So that's saying that the Laplace transform of f of a times the Laplace transform of f of b actually equals the Laplace transform of the convolution of f of a and f of b. Now let's be a little bit clever. Let's replace the Laplace transform of f of a with capital F of a. Yep. And times that by the Laplace transform of f of b, which we're going to use as a capital f of b, equals the Laplace transform of f of a convolved with f of b. Yeah? So I'm just using the normal Laplace transform notation here. So when we have f of t in Laplace, if we convert that, we do the Laplace transform, it's going to be f of s. So what I could do is, yeah, let's leave this as f of a and f of b. Well, what we would really normally do, actually, we would say it slightly differently. We would say the f of s. No, we can say that. That's fine. So we've got two Laplace transforms here, f of a and the Laplace transform of f of b equals the Laplace transform of the convolution of f of a and f of b. Therefore, if we took the inverse, and this is where it comes in really, really beautiful, if we take the inverse of f of a times f of b, that's going to be equal to the inverse of this. And the inverse Laplace transform of a Laplace transform cancels all Laplacian operation, so we're left with the convolution of f of a and f of b. In other words, the inverse Laplace transform of something like f of s times g of s is going to be equal to f of t convolved with g of t. Now I'm going to do that again just for clarification, and hopefully it will make a little bit more sense. So if we have, say, the Laplace transform of f of t dot times the Laplace transform of g of t, we can say that that's going to equal the Laplace transform of the convolution of f of t and g of t. Yep. Again, we're not interested in what convolution is. We're just looking at a principal identity that's going to show us why it's so useful in solving inverse Laplace transforms. So we've got the Laplace transform of f of t dot the Laplace transform of g of t equals the Laplace transform of f of t convolved with g of t. Now, how do we normally write the Laplace transform of f of t, and how do we normally write the Laplace transform of g of t? Well, we can just write it like this, can't we? F of s dot g of s. And that's going to equal the Laplace transform of f of t convolved with g of t. Now, if we take the inverse Laplace transform of the left-hand side, we'll have to take the inverse Laplace transform of the right-hand side. And you see here, we've got a forward Laplace operation and we've got an inverse Laplace operation here. So that will cancel all Laplace operations on the right-hand side. And we're left with saying that the inverse Laplace transform of f of s dot g of s equals f of t convolved with g of t. That is the most important result in convolution theory that I know of at the moment. Because what it allows you to do is that it allows you to have any two functions. You don't even need to know what they are, whatever they are. And if you want to know the inverse Laplace transform of two functions, they can be very complicated. You might not know how to put them into partial fractions. You might not have a clue how to get them into a way of identifying the second shift theorem or the first shift theorem. And if you can't do that, the convolution theorem allows you to easily find the inverse Laplace transform of any two products. All you have to do is find the inverse Laplace transform of one product, f of t, and the inverse Laplace transform of the other product, g of t, and convolve those two functions together, and that will give you the result. Okay, so before diving in to the definition of convolution and what convolution is, there's some very important background that we need to ensure that we understand before moving on. Very simple theory, but it's extremely, extremely important in convolution. So let's have a look. Now, if you can see the blue line, that's just the sine t function. And the dotted line here is t equals pi on 2. So it's the first quarter cycle of the sine wave. And I just want to go over what shifting functions mean and what they look like. I know that sounds very simple, but it's going to get a lot more complicated very quickly. So I want to go over the principles from basics to begin with. So we see we've got sine t over here. We've got the t equals pi on 2, the dotted line. And if you look at the orange line, sine t plus 1, what that does, it shifts the sine wave to the left. And that should be quite intuitive now. That should be quite easy to grasp. If we have sine t minus 1, we move the sine wave to the right. You can see the yellow wave has been moved by 1 second to the right. Can you see that? So again, if we've got a positive shift, it means the function has been shifted to the left. We can see the blue line to the red line, it's been shifted to the left. If we're going, if we've got a negative shift, it means the function is being shifted to the right. So you can see from the blue line to the yellow line, it's being shifted 1 unit in the right direction. Now, this is when things get a little bit more complicated. What happens when we have a function that has been reflected in the y-axis? Does a positive shift mean going to the left or going to the right? So if we have a look at the blue dotted line, that's our sine t function over here. We've got t equals pi on 2, so for the first quarter cycle. And then we have the red line, which is sine minus t. So sine minus t is a reflection in the y-axis. So if you can just take a moment to notice that, got the red line here is being reflected in the y-axis. Now, what does the yellow line look like? Sine minus t, so that's exactly the same as the red one, but with a positive shift of 1. So we've got sine minus t plus 1. So normally, intuition should state that we move the function to the left, as we did previously. But that's not the case anymore. Can you see as we're going from the red line to the yellow line, once we have a reflection in the y-axis, we can see that if we add a positive shift, we are now shifting the function to the right. And that is a very, very important principle to get into your understanding, to get into your head when we're doing convolution. That is extremely important. When we have a positive shift, we actually move to the right after we have reflected the function in the y-axis. So if we reflect the original function in the y-axis and then have a negative shift, i.e. let's say it was sine minus t minus 1, it would actually move to the left of the red line. So again, just to say that once more, if we have a reflection of the function in the y-axis, a positive shift will result in the function moving to the right, a negative shift will result in the function moving to the left. So what is convolution? So convolution is, in essence, very easy to understand. It's not difficult. Convolution is a function that describes the magnitude of the AOC, or the area under the curve. Or, another way of saying that is that a convolution of two functions is a function that describes the magnitude of the area of overlap between two functions for all values of t, all values of those two functions. So what that means is that if you take two functions and you keep one function fixed in one position, so you don't need to worry about that one, that's good. The second function, you want to take it and slide it across the entire first function, and for every value that you slide that second function across the first function, you want a description of the magnitude of the area of overlap between those two functions. And it's as simple as that. So let's try and build a mathematical tool that we can use to describe and to perform that operation. Okay, so let's have a look at two functions. We've got f of t and g of t. Don't worry about the values for now. What we're trying to do is build up a mathematical way that we can work out a function that will describe the area of overlap, the magnitude of the area of overlap for all values of t as one function is swept across the other function. So we have two functions here, f of t and g of t. And we want to try and find out, I know I'm repeating myself a lot, but this is a little bit tricky, in my opinion. We want to find out the magnitude of the area of overlap for all values of t as we sweep one function across the other. So whenever we're trying to describe an area under a curve or under something, we know that we're dealing with some kind of an integration. And we want to know the entire area of overlap for all values of t. So we know that it's going to have something to do with an infinity and a negative infinity. And we're interested in the magnitude of the area of overlap of those two functions. In other words, we're interested in the size of the product of those two functions as they cross each other. So, for instance, in this position, the area of overlap would be g of t times f of t between this point over here and this point over here. And as you can see, if we shift this red function from here to here, it's actually going to remain constant for those values of t, isn't it? We can see that, yeah? So we're going to involve some kind of product of f of t and g of t, dt. Something like that. And that should give us some kind of what's going to give us the product of those two functions. And it was in something involving positive infinity and negative infinity. I know it sounds very vague at the moment. But we're building up a model here. We're building up an idea. So how are we going to do this? Well, one idea could be to, and this is very clever, if we reflect the second function, let's say that we're going to be sweeping the red line function. We're going to always keep f of t where it is. So that's nice. F of t can stay where it is. So if we flip the g of t function in the y-axis over here, what we can do is flip it and then we can sweep it across. Because if we sweep it across at the moment, we can see that we're missing out on everything that would happen from here to here. Because there's going to be some magnitude variation in the area of overlap if that red box started from over here. As we move it across, the area of overlap is going to increase and increase and increase. It's going to increase like this, and it's going to increase like that, all the way until it gets to this point over here. So one thing that we can do, I've mucked up the drawing now, but if we flip this red line function in the y-axis, that would be a good starting point. So let's go ahead and do that. So we've got our integral, positive infinity and negative infinity. F of t doesn't change. And now we can say g of minus t. Because remember, we haven't changed the function, we've just moved the function, we've reflected it in the y-axis, dt. Now that we've done that, we have this. We have f of t, which is unchanged, and we have g of minus t. And g of minus t is just g of t reflected in the y-axis. And that's what we have here. Now, going back to the definition of convolution, if convolution is defined as the magnitude of the area of overlap between two functions as one function is swept across the other function, we have to find a way of describing what the magnitude of the area of overlap is for all values of t. In other words, convolution is a function. It's not a static value. Convolution is a function that describes the area of overlap for all values of t as one function is swept across the other function. So we have to find a way of sweeping this function. We've got it in a good position now. We've got f of t, g of minus t, because now it's in a position where we can actually sweep for all values, and we're not going to miss anything. But we have to find a way of sweeping this function to the right, so that for every value of t, let's say, t is 0 over here. I know that's an obvious point, but it's not going to be so obvious in a second. Here is t is 0. As t increases in value, that box is going to move further and further to the right. As that box moves further and further to the right, there's going to be more and more overlap between those two functions. So the convolution function is going to increase as this red line starts to move across. The blue function, yeah. So how are we going to find a mathematical way of finding the area under the curve, or the area of overlap, which is the product of those two functions, as we sweep t across? That's the question. So to do that, we can introduce a dummy variable. In some mathematical textbooks, that's an x, and in many engineering textbooks, that's a tau. So you can use whichever you feel comfortable with. But if we change the axis to a dummy variable and do something else, which I'm going to speak about in a second, we can start to be very clever in how we're going to find the convolution function. So let's go ahead and do that. This is f of tau, and this is tau. This is g of minus tau. So g of tau would just be the reflection in the y-axis of what the original g of t was. And all I've done is just replace the axis with t is tau, and the function argument with tau instead of t. And the reason why I've done that is for the following. We can now say something like positive infinity and negative infinity, f of tau times g of minus tau d tau. So I haven't actually changed anything really from here to here. In fact, it's blinking identical. The only thing that I've changed is the scale. I've introduced a dummy variable tau, but I haven't changed the function at all because this is f of tau. This is g of minus tau. It's exactly the same as g of minus t with the scale at t. It's exactly the same. So we've got the product of f of tau and g of minus tau d tau between positive infinity and negative infinity. But do you remember we said how important it was to find a way of sweeping this g of minus tau across the first function of f of tau for all values of that axis. What is that axis? Is it tau or t? Well, we changed it to tau, but we needed to find a way of sweeping that function, that red line function, across all the values. The way we do that is by introducing this dummy variable of tau. What we can do is something very clever. We can say that the convolution will be the infinite integral of the product of f of tau and g of minus tau. But what we're going to do is be very, very clever here, and it's actually beautiful to be able to experience this. If I understand it correctly. If we write a t just over here, just like that, that t is not part of the integration anymore. However, what that allows us to do is sweep this second function of g of minus tau across all values of tau. Why? Because when t equals 0, when tau equals 0, the position of this second g of minus tau function is going to be over here. As t increases, and this is where the magic happens, as t increases in value, we're going to get the function description of the magnitude of f of tau times g of minus tau for all values of tau. For all values of tau. Why? Because when we perform the integration, we're going to be left with a function that involves t. And that function is going to be exactly this thing of f of tau, g of minus tau, in terms of t. So we now have something beautiful. We now have a description, a function that describes the product of the area of overlap between two functions for all values of t, between positive infinity and negative infinity. For instance, when t equals 0, we can see that the product of f of tau and g of minus tau is 0, because the area of overlap is 0. So when we actually end up with our function description, our convolution function, it's going to be 0 when t equals 0. As t starts to increase, and the red box is moved to the right, the convolution function will start to increase until it gets to a certain point at which it's maximum. When it's maximum, as you move the red box across even more, it's not going to increase because it's assuming that the red box is smaller than the blue box. So we're going to have something that looks like this. And then, as the function, as the g of minus tau is moved beyond, then the product, the area under those two overlap is going to reduce to 0, eventually like that. But the point is that this is a really beautiful description of how you can find the magnitude of the area of overlap of any two functions for all values of t by introducing this dummy variable and integrating the product. So a good way to try and understand this principle of convolution is just by going straight into an example, and we'll see if we can use the theory that we just covered to work out what the convolution between these two functions are. So we've got here two functions. We've got f of t and g of t. F of t is the blue line, and g of t is the pencil line over here. Okay, which is just a description here. So we've got f of t is 2 between the values of 0 and 3, and 0 for all other values. And for g of t, the function is 1 between 0 and 2, and 0 for all other values. And the question is, what is the convolution of those two functions? So what we're really looking for is a convolution function that describes the magnitude of the area of overlap between those two functions as g of t is swept across f of t for all values of t. So the approach to this question involves going back to what we said, first of all, about how do we come up with a convolution function, the description. So do you remember, first of all, what we did is that we flipped g of t in the y-axis. So if we just write down that the convolution function is going to be equal to f of t star g of t, or asterisk g of t, which is going to be equal to, if we're using tau, equals minus infinity and positive infinity of f of tau g of minus tau plus t d tau. So let's think about this. So the first thing that we have to understand is that we've flipped g of tau in the y-axis. That's why I've got g of minus tau. So let's draw that. Okay, so we can see here we've got f of tau unchanged, takes the value of 2 between 0 and 3, and we've got g of minus tau, so I've just flipped that in the y-axis over here. And what we want to do is sweep g of minus tau across f of tau for all values of t. So the approach here is to split this question up into different parts so that we have different integrations, and we can therefore work out what the function descriptions are going to be for each phase of the motion of the sweep. So we can say that when we flip g of minus tau in the y-axis, t is going to be 0 over here. This is the leading edge. The leading edge is going to be 0. Say t equals 0. And as t increases between 0 and a certain value, we can say that the function, the convolution function, is going to increase. So we can say that the convolution function is going to be between the values of, remember, t is increasing, so it will have to be between t and 0. Because remember, we're interested in this little window that's getting larger and larger and larger and larger and larger. And this window that's increasing is what we're trying to find the integration of. So it's going to be between the t value and 0. It's not going to be between the t value and here. Because between here and here, it's going to be 0. Remember, it's the product of those two functions that's going to give us the area of overlap, or the magnitude of the area of overlap. So it's going to be between t, as t starts to increase, and 0, as this red box starts to move to the right. So, but remember, it's only going to be true up to a certain point, because it's only going to be increasing up to a certain point. So we can say here that the convolution function is going to be t is going to be evaluated between t and 0 as t increases and increases and increases, and it's going to be f of tau. F of tau is going to be 2. We can see that it's going to be 2 dot g of t minus tau, which we can see is going to be 1. Okay, because that has the value of 1, because g of t is 1 for between 0 and 2. So it's going to be 2.1 d tau, but that's only going to be true up to a certain point between t equals 0 and t equals 2, because when t equals 2, that red box is going to be fully enclosed and it's not going to be increasing anymore. So this is going to be true for t goes up to 2 and 0. Once t equals 2, we're going to have to look at what the convolution function is going to be then, and you'll see why it's going to be different in a second. So if we just evaluate this, that's going to be equal to, between t and 0, of 2 d tau, which is going to be equal to 2 tau, evaluated between t and 0, which is going to be equal to 2 t. So we can say that between 0 and 2, the convolution function, it should be 2t, which kind of makes sense because we can see that the magnitude of the area of overlap is going to be increasing as this red box moves into the blue box, but only up to a certain point, up to when t equals 2. Let's have a look at what happens after t equals 2. Once t equals 2, we can see that as the red box moves to the right even further, the magnitude of the area of overlap, which is here, is going to remain the same as the box moves, at least until t equals 3. So we can say that the convolution function is now going to be t, because remember t is dynamic, it's going to be moving. That's going to be tau equals t, from tau equals t to tau equals t minus 2, because whatever the value of tau is over here, of t is, sorry, over here, that integration point is going to be 2 stops behind, and that's moving dynamically. That's the point over here. We can see this red box, once it's fully enclosed, is moving dynamically. Previously, that was not the case. The only thing that was moving dynamically was t over here. As t gets larger and larger and larger, that box gets bigger and bigger and bigger. But we're measuring it from t and 0, not t and 2 stops behind t. Because 2 stops behind t, you're going to get 0 over here. There's nothing. We're only interested in this box that's getting larger and larger. Over here, this is a dynamic box from 2 ends. And that's a really important point. And this is where it gets a little bit confusing. That you have to be very careful with the point that you choose for the limits. So in the middle, because t is moving dynamically over here, meaning that we're trying to evaluate the magnitude of the area of overlap as t moves over here, and it's between t as it moves between here and here, and t minus 2 as it moves across as well. That's why it has to be between t and t minus 2. And the function of tau is going to remain constant at 2, and the function of g of minus tau is also going to remain at 1 d tau, which is going to be 2 tau evaluated between t and t minus 2, which equals 2 t minus 2, which equals 2. T minus t is 0, it's 2, and that equals 4. So we can say for t being between, where did we leave off? 2 and 3, c of t equals 4. Okay? Now let's have a look at what happens as that red box has now moved to completely the other side. So now the red box is actually going to be, I'll do that in a pencil actually, so maybe it's a bit clearer. So once it's moved to here, to that point, what's going to happen as the box moves even further to the right? That's what we're going to have a look at next. Okay, so now we can see that the t is at position 3, and we want to know what's going to happen after t equals 3. Now, an important point to note here as well is that, and it goes back really to the definition of the convolution theory, is that g of minus tau plus t, the reason why we can say plus t is because it's a reflection in the y-axis. And remember what we said, that if you do a positive shift, it's going to move the function to the right. That's why we're doing plus t and not minus t. And that's why I try to explain at the beginning, that when we have a function that's reflected in the y-axis, you must have a positive shift of plus t to move the function to the right. So, so let's think about this now. So the function is over here, and as it starts to move out, as t increases and it gets larger and larger, because remember that's what we're trying to find this function for as t increases. So so when t starts to increase, this is going to move further this way, and the area of overlap is going to be f of tau, which is 2, dot f of g minus tau plus t, which is going to be 1 d tau. But what are the limits going to be as it starts to exit? So we know that the lower limit has to be 3. Is that right? The lower limit has to be 3? No, that's not right. The upper limit has to be 3. Because remember, beyond the limit of 3, the area of overlap is 0. So that's not good. That's not what we're interested in. The upper limit is going to be 3. The lower limit is going to be whatever this line happens to be in terms of where t is. So at the beginning, when t is 3, this needs to be 1. When t is 4, the box is going to look like this, isn't it? So it's going to be between 3 and 2. When the box is almost out of the picture, and we're up to 5, it's going to be just before 3. So we can say that the lower limit is going to be the t value minus 2. So when t is 3, the lower limit is going to be 1. So we're going to be integrating, we're going to be finding the area of overlap, the product of these two functions. As t starts to increase, right, we're taking always the upper limit as 3, but now we're only interested in like this area. As t increases, we're only interested in this area. As t increases even more, we're only interested in this area. As t increases even more, we're just interested in this tiny little sliver over here. So that's why the lower limit will be t minus 2. I hope that was clear. So let's go ahead. So that's going to be 2 tau evaluated between 3 and t minus 2, which is going to be 2. 3 minus t minus 2, which equals 2. 3 plus 2 minus t equals 2. 5 minus t, which equals 10 minus 2t. And that's the convolution function for t is starting at 3, because that's where we left off, and it's going to go up to 5, because at 5 it's going to be 0. So those are the, that's the summation of what we found. Between 0 and 2, we found the convolution function was 2t. Between 2 and 3, it was 4. Between 3 and 5, it was 10 minus 2t. And for all other values, it would be 0. So let's draw that out and see what that looks like. And there we have a graphical representation of the convolution function that we were able to find for those two box functions as one swept across the other one. So I hope that was clear, and maybe watch this one again, and in the next video I'm going to be looking at a more complicated example of deriving a convolution function.